I guess now you can hear me again.
Yes, but
Yeah.
we cannot see.
Sorry. I share again the screen. Now you see it, right, Marta?
Yes, yes, please. It's for the recording, I think. Sorry.
Okay, no problem. So, yeah, agenda for Design Meets Steel is a brief introduction. I talk about the advantages of conformal cooling. I show you how we design those channels and how we simulate them. We talk about the sufficient material selection. And in the end, there is a short summary, and we are open to answer your questions. So first of all, why do we need contour temperature control? And this is a really important question because there are several advantages. A really big advantage is the increase in quality. So with the conformal cooling, we have often a reduction of scrap rate. We are reducing the hotspot, and we have a better part quality because of the thermal management of the mold. We also can increase the productivity. There is one productivity increase regarding the cycle time. Typically, we do not affect that much the solidification time. If we have a reduction in cycle time, it's mainly due to the spraying time, which can go to minimal or micro spraying. But what's also is important that we have reduced cleaning effort. So we have fewer machine stop. The worker does not have to stop the machine, clean a specific area, and then the production can start again. So with conformal cooling, we have less sticking of the aluminium. We also have an extended lifetime of those inserts, but you need to two important things take into account. One of all, of course, you need to use the right steel powder. I will talk about that later. And the thermomechanical stresses, which are in the process and also related to the conformal cooling, they also need to be optimized to get a sufficient lifetime. And last but not least, sustainability. We have a more efficient production. If you spray less, you also waste less material. And of course, if we shorten our production chain, that's also more sustainable. But a big increase is in the foundry where we really can reduce the scrap rate, and that's a big effort for the sustainability. But all in all, we use the conformal cooling to reduce the total cost of ownership in the foundry per produced part. Here is one example. This is a slider, as you see, with a contour temperature control. Here is the calculation. The hourly machine rate was approximately 300 euro. Cycle time was 73 seconds. We had the utilization rate of the machine 77%, and all the variable costs are calculated with approximately 25 cents per shot. And we had conventionally 8.2% scrap rate. And with the conformal cooling of the slider, you see here the scrap costs were reduced by 160,000 euro, as we had lower than 4% scrap. Of course, there were some additional costs for this slider, for the conformal cooled slider. So in total, it was 39,000 euro for, I didn't mention it, 450,000 aluminium parts. And then there comes the cleaning cost inside. Conventional, it was 21 minutes per shift, and with the conformal cooling, we now had reduced it to 7 minutes per shift, and this was a saving of 9 cents per part. So in total, 40,000 euro that were saved. And you see, the cleaning costs covered totally the cost for the conformal cooling. And if we make a overall calculation, the profit with the conformal cooling was 170,000 euro. Another case study is housing with ceiling roofs. Here you see the 3D model. Here you see it on the aluminum part. The reason why we put below here a conformal cooling was that the customer wanted to reduce the scrap rate and also wants to reduce his downtime to prolong a longer lifetime. What we get was a scrap rate reduction by 4%. We had less cleaning required, but most important for him was that they had no reworking on the ceiling roof on the casting. And conventionally, they had to, after 4,500 shots, they had to rework really every casting. And that's a massive cost driver if you rework all the castings. And yeah, this was a really, really huge benefit for him. We also increased the lifetime, like from conventional 90,000 shots up to 48,000 shots. But as I mentioned, this was the biggest argument for the customer. The other things were nice to have, but really that he got rid of the rework. It's a bit long ago, this case study, but that was a really, really big success for him. So how do we achieve these results? And the base is really our customer intimacy. We are close to the customer. We talk about the customer. You know your processes better than we, and there needs to always be an interaction that we can supply tailor-made solutions. What we offer is then the optimized powder. The powders are really made for die casting, so really tool steel powder. We have the optimized design, and there we are taking also the periphery and your needs into account. I will talk about this in detail on one of the next slides. Then we are printing with highest quality and reliability, and in the end, every insert is a tailor-made solution. And together with you, our customers, we develop this tailor-made solution for your problem. Yeah, let's talk about the design and simulation. Before we get to the optimized design, there are some questions that need to be answered. The first one is, why do you want it? Do you want to reduce scrap rate? Do you want to increase part quality? Do you want to improve cycle time? Whatever is the reason, there are multiple reasons. Yeah, we need to know it. Then, how does the periphery look in the foundry? It's important to take that into account. Do you use oil or water? At which temperature? How they are in the operations and connected, and all of this is very important that you have. Then we can go in the simulation. As more data you provide, the better the simulation results will be. There we can, for example, compare existing solution with the new design and the conformal channel design. And it's important that we adapt this design to your periphery and also to your request and your need. So really every insert is its own temperature control system to suit your needs, and it needs to fit to the whole mold. That's important. How we do it, if we get the casting, here you see the thermal load, and there we identify certain hotspots. We are taking these thermal loads into account, and then we are designing those channels. For example, here where it's hotter, red, we put some more channels as compared to this area where it's more green and blue. There it's a little bit colder, and there we don't need that much heat taken out. If we design those channels and we do a parallel channel design, here you see the parallel channel design, it's always important that the channels are balanced. That means that in every of those 3 channels runs the same water or oil. Yeah, that's important that not just one gets all the water or all the oil and the other 2 are neglected. Here you see the velocity. This is yeah, a typical flow analysis that we do to balance those channels. And here you see, for example, a comparison. Here was a major hotspot, and we reduced it here. It's important that you don't need too cool, too hard, because that's bad for the steel. If you put too much energy out, then the steel gets too cold, and that's also not good. So it needs to be on the right level. Here is one interesting slide where you see here the temperature and the time. This curve is for drilled cooling channel, and the upper curve is for near contour channels. And you see that's important, the average temperature in this insert. And here you see, even with drilled coolings, the average temperature is colder than with the near contour temperature control. That's okay, because the near contour temperature control takes the energy out where it appears. So close to the contour, where you get a lot of heat impact, there you get it out. And also the steel likes to be more warmer, because then we have better toughness and yeah, these better mechanical properties. And the more cooling, it's not better. You need to adapt the cooling to the right hotspot and there suck out the energy of the shot. And that's really with the near temperature control, you can apply the perfect thermal management for the whole mold. Another important factor is the stresses. You have 2 stresses, more or less, thermal stresses and the mechanical loads. So together they are the thermomechanical loads. And you have stresses that come from the cavity. Actually, you can't influence them by the design of the aluminium part. But you also have stresses that are created from those cooling channels. And it's important that you do not have here an overlap and the stresses are not too high. So this is done via simulation. There you see those results. And what our designers do after they simulate it, here you see they make some small adjustments of the channel to get down those stresses. And stresses means in the end longer lifetime. And that's important that yeah, you do this stress calculation to improve the lifetime. How we do it? We do a stress analysis, then some minor changes. Here you see some minor changes of the channels. We do again a thermal simulation, adapt the channel design, and these are several loops. Sometimes it's 2, sometimes it's 5, depending on how complex the channel geometry is and the part geometry is. But with the loop iteration, yeah, we get an extended service life with our solutions. That's besides the premium powder, a very important factor to get it to design. What can we build? If we have here the build platform, and the angle is more than 45 degree, less than 45 degree, sorry, we need support structures, and that's important. So with an angle bigger than 45 degrees, we can print it without support structures. You also can implement different cooling channels. You have round cooling channels, elliptic cooling channels. Yeah, a lot of variations, but important. Always take the stresses into account. Elliptic shape has other stresses than a circle, and yeah, there really the stresses are very, very important. Hole diameter, typically it's 1.5 up to 8 millimeters that we can print. 8 millimeters is very sell them because typically, there you can also work with a conventional cooling. So in most of the time, it's somewhere 4 to 5 millimeters. We can print small overhangs, 0.5, but you should avoid them. That's more on the safe side. Another important factor are the radii. Here you see the notch impact toughness, and you see a radii of 0.25 millimeters. You have 7 joule. If you increase this radii up to 0.75 millimeters, you more than 3 times the notch impact toughness. With the same steel, same heat treatment, everything, just changing the radii is very important. And below 1 millimeter, every 0.x counts. As you see it here, there's a huge ramp up. So if you are designing an aluminium part and you can live and you put a 0.2.5 radii there, maybe 0.7 would be also sufficient, or 0.3, 0.5, whatever. Please take this into account. This is not just important for the channel design, but also for the cavity design. And if you have parallel channels, you need to control them individually. Here, you don't know if the uppermost one is blocked or not. So please put them that you can control them from below and prove them separately. That's really important. We can also do hybrid manufacturing. There we have a conventional part and we print just where the conformal cooling is needed. One important thing is always use the same type of material. That's really, really important. Otherwise, you will get issues. So to summarize, a suitable design extends the service life, but you have a sufficient cooling performance. If we are now taking to the material selection, here you see as a benchmark H11, so 1.2343. This was done at the Austrian Foundry Institute. And we checked here the resistance to thermal shock. Here you see the analysis. We checked here W360 bulk material and also W360 printed material. And here you see both steel perform better than a typical 1.2343 bulk material. And also you see some use the 1.2709. For printing, you see they are worse than the W360 and the 1.23. And so this is one material, the W360, which we recommend. Another material is the Diver. And here you see again the 1.23 as a comparison with the toughness. And with Diver, we are getting double the toughness of a ESR grade 1.2343, and that's important. So here a slide table about those graphics. To summarize it, if you need toughness, we typically go for a Diver. If you need more wear resistance, then we typically go for W360. But both materials are superior solutions to 1.2709 and also to 1.2343 ESR. Afterwards, we have the printing. We have an offset of 1 millimeter for our materials. They need to be reworked afterwards, so turning, milling, EDM, whatever needs to be done. We can even do polishing and coating, for example, also texturing of some parts if you need it. We have a production depth according to your requirements. Whatever you want, a part with offset that you rework or the ready-to-use part, we can offer this solution to you. Coming to the end, It's really important that we reduce the cost in the foundry, so the total cost of ownership per produced part with the improved quality, improved productivity, and the extended lifetime. How we do it with the thermal management of the mold through temperature control, design analysis, and you saw the effort that we put into to optimize the design, and also with the right steel selection. These are really important things. And with this, we get lower scrap rate, so a better part quality, less sticking of the aluminum on the steel, so a higher productivity and less heat checking because we are taking the energy out and the energy is not via spraying taken out. So the casting quality, process stability, and of course the mold life will be thankful for it. And as said, voestalpine is your partner for close contour temperature control in die casting. Thank you very much for your attention. And Marta, I think now we are going to the questions, right?
Yes, yes. If anyone has question, please use the chat or raise your hand. In the meantime, here two contacts for projects or have more information about voestalpine and die casting. Region EMEA, sorry, Luca, and for India, Manish. And I can see the Zurro Davide have question, please.
Ciao Johannes and Marta, thank you for the presentation. I'm just curious about which software you use for simulation and for CAD design.
For the simulation, we are using Siemens NX, and also for the stress analysis. We can support on the Magmasoft, but the actual design we are doing with Siemens NX.
Any other question? If not, as I already mentioned, you've got the right contact in this chart. And thank you so much for joining us in today's webinar. And have a good rest of your day.
Thank you. Have a nice day. Bye.
Bye.